Welcome to Hart und Trocken. In this video, I want to give you an introduction to functions of one variable, along with some basic definitions. In the most general sense, a function is a relationship between two variables. That relationship is typically asymmetric. That means one variable depends on the other one, but not vice versa. In some cases, we can define a function with a table. That means for each value of the first variable, we can write down the value of the second variable. Provided that it is possible to write down all values of the first variable in a table, that table completely defines the function. Now, the relationship between the two variables being asymmetric implies that one variable depends on the other variable, which is why we call the variable which depends on the other variable the dependent variable and the other one the independent variable. So many things in the real or in the mathematical world can be represented by functions that it's hard to categorize all fields of applications of functions. Let's look at an example. The graphic you see is the number of Google searches for the term quadratic formula. Here, the time on the horizontal axis is the independent variable, and the number of Google searches on the vertical axis is the depending variable. It's interesting to observe that apparently the number of Google searches for the term quadratic formula is low in summer and high in September. Apparently, people are not as interested in quadratic formulas during the summer break as after the summer break. As you see in this example, it is also very common to picture or to think of a function or to even define a function using a graphical representation, which we call a graph. An example where it's useful to use a table to describe or to define a function might be the world population in different years. Here, the year or the time is once more the independent variable, whereas the population in millions is the depending variable. One important characteristic of a function is that each value of the independent variable is assigned to a unique value of the dependent variable. So in this case, you see each year which is written down in that table has exactly one number for the population in millions in that given year. By the way, it is not necessary that on the left-hand side we write down each and every year. The 6 years we have chosen here don't even have equal distances between each other. Still, this table defines a function. Most typically, however, functions are defined using formulas. In this case, we have written down the formula for the area of a circle with radius r. So the formula reads that for each given value of a radius r, the area of the circle with this radius can be computed as pi times r squared. In this case, the radius r is the independent variable, whereas the area A is the dependent variable. In order to denote the dependence of one variable of the other, we typically write the independent variable in brackets after the dependent variable. In this case, this would be A followed by an r in brackets. Now let's try to summarize what we have just learned about functions in a precise mathematical definition. We say a real valued function f of a real valued variable x with domain D is a rule that assigns a unique real number to each x element D. Now the most important part is the one which I have put in that blue box. It's a rule that assigns a unique real number to each x element D. Unique means that we are not allowed to assign more than one real number to a given x element D. That uniqueness requirement is important when we need to decide if something is a function or not. Next, let's look at that word domain D. The domain D is the subset of the real numbers on which the function f is defined. That means there is some rule which assigns to each one x element D a unique real number to that x. The domain D reflects the idea that there are functions which are not defined for every real number. Rather, they are only defined for a subset of the real numbers, for instance, only for the positive real numbers. Now, such a value, which is assigned by the function f to some x element d, is called a function value or the function value of x and is denoted by f of x, which means f followed by an x in brackets. We call the set of all resulting function values f of x the range of f. The range is some sort of footprint of the function. So if we run through all x element d and log the resulting f of x for all these x element d, the altogether result, that means the set of all these values, will be the range of x. Typically, that rule that assigns a unique real number to each x element d is encoded using a mathematical formula which involves x. As an example, let's look at the function f, which assigns to any number its third power. We typically define this function by defining the function value of x using a formula involving x. In this case, f of x equals x to the third power. Alternatively, we could use the following notation. We read this as the function f is defined as an assignment which takes every x to x to the third power. Note the arrow with a little extra vertical line. Now, given that definition of the function f, we can evaluate the function f for different values of x. Now, how do we name functions? Well, f is a very typical function name, but if we want to write down several functions, we need several function names. Typical function names are f, g, h, capital F, or Greek letters like phi. Now let's repeat a little what we've just learned. F followed by x in brackets is pronounced f of x or sometimes fx. F itself is the function, whereas f of x is the function value. If we introduce the variable y and set it equal to f of x, then x is called the independent variable and y is called the dependent variable. Finally, if a function is defined as f of x equals x squared plus 5, then the function f is the rule which assigns to each x the expression x squared plus 5. To summarize our earlier example, let f be the function that assigns any number to its third power. We then write f of x equals x to the third power. By the way, it's important to note that f of x equals x to the third power does not imply that f of x plus 1 equals x to the third power plus 1. The right value for this is rather this one. Now let's have a look at another example for a function, this time taken from economics. It's a function which assigns to the number of units x of a product the total cost of producing these units. It is defined by c of x, where c stands for costs, equals 100 times x times square root of x plus 500. By this formula, we are able to calculate the production costs for any given number of units x. Let's say we want to find out the cost of producing 16 items. For this purpose, we replace x by 16 and calculate the result. We get this expression, and we can further calculate 100 times 16 times 4, which is the square root of 16, plus 500, and which simplifies to 6,400 plus 500, which ends up in 6,900. So the production cost for 16 units is 6,900. Now, instead of replacing x by a specific number, we could also replace x by some other variable. Let's for instance say we want to know the following. If we usually produce A units, what is the cost increase if we start producing a plus 1 units. For this purpose, we both calculate c of a and c of a plus 1 and calculate the difference between those two. So first, calculating c of a gives us 100 times a times square root of a plus 500. Calculating ca plus 1 gives 100 times, now in brackets, a plus 1 times square root of a plus 1 plus 500. Now we have to carefully write down the difference between those two, which is first, the second line, so that is 100a plus 1 times the square root of a plus 1 plus 500. And now we have to subtract c of a, which is 100, put it in big brackets, times a times square root of a plus 500. And now, well, usually we say now we have to only simplify, but sometimes there's hard work in simplifying. Let's try to do that here. So we first note that we have a plus 500 here, and then there's another plus 500, but it's contained in a minus bracket. So actually that is a minus 500, and this cancels away with this plus 500. So in the next step, we can just omit these two 500s. So the remaining expression is a difference containing these two expressions. And you see that both of them contains a factor of 100. So we can at least factor out that 100 in the next step. In fact, this is the best we can do here. This expression gives us the information that if we initially produce a units, what is the increase of cost if we start producing a plus 1 units? This is, by the way, also a function. It depends on a, and we could give it a new name, something like I for increase. Now let's talk a little about the domain and range of a function. If a function is defined by a formula, the domain are the set of all independent variable values for which the formula gives a unique value. Let's look at some examples. For instance, fx equals 1 over x plus 3. In order to find the domain for this function f, we have to find all values of x which give a unique value using that formula. Well, the uniqueness is not a problem here. So if the formula gives a value, that value will be unique. However, for certain x there might be a problem of giving a value at all. Remember that in a fraction like this, the denominator never must be 0. If the denominator turns 0, the fraction is not defined. That means the formula doesn't give a value. That means we have to rule out that the denominator gets 0. So in turn we pose the question, when does the denominator turn 0? Well, when the expression x plus 3 turns 0. Obviously, that is the case if x equals minus 3. So we have to exclude the value minus 3 from our domain. All other real numbers for x are not a problem. So the domain is all real numbers except for minus 3. Using set notation, we can write this like this. The domain D equals all r except for minus 3. Let's have a look at another example. G of x equals square root of 2x plus 4. Following the strategy of the first example, we have to exclude all values for x, for which this expression doesn't give a value. Now we know that in the real numbers, the square root of a negative value is not defined. That means the expression under the root 2x plus 4 may only be 0 or positive. So 2x plus 4 must be greater than or equal to 0. Solving this inequality for x gives us 2x is greater than or equal minus 4, and dividing by 2 gives x is greater than or equal minus 2. That means in order for the formula for g of x to give a unique value, x has to be greater than or equal minus 2. In other words, that means we have to exclude all x which are strictly smaller than minus 2. Using set notation, this gives for the domain D Well, the interval going from -2, and the edgy bracket means that -2 is included in the interval, well, until infinity, positive infinity. And as infinity is never included in an interval, as it cannot be included, we use these brackets. That means that the interval is half open on the right-hand side. Now let's talk about the range of a function. The range are the set of all real numbers y, such that y is the function value of f for some x element d. Using set notation, this gives the range R is the set of all y element R, such that is denoted by that vertical line, such that y equals f of x for some x element d. Let's have a look at some examples. We want to show that 4 belongs to the range of g of x equals the square root of 2x plus 4. So in other words, we want to check if there's some x in the domain of the function g such that g of x equals 4. So remember that that function g is exactly the function we used in the last example. So we already know the domain of g, which is this one. Well, what we now want to know is if there is some g of x which equals 4. That means if there is some square root of 2x plus 4 which equals 4. Now we have to solve this equation for x. We can take the square of both sides. Yeah, so we take the square of both sides, which gives 2x plus 4 equals 16. Now if I subtract 4, get 2x equals 12, which is x equals 6. So we have found that it is g of 6 which equals 4. So the question was if 4 belongs to the range of that function g. And the answer is yes, 4 does belong to the range because there is a real number x, which is 6, which belongs to the domain of g and which is taken by g to the number 4. We now want to know, well, what is the range of g of x? So we want to calculate the range of g of x. In order to figure this out, we have to walk through the real numbers, and for each real number we have to ask ourselves if this expression can take on this value. Now first remember that the square root of some number can usually take on positive and negative values. For instance, the square root of 4, understood as that number which, when squared, gives 4, can of course be plus 2 as well as minus 2, because the square of both of these numbers is 4. However, the convention is that when using the square root symbol, we rule out the negative solution. That is the reason that, for instance, square root of 2 cannot be confused with minus the square root of 2. This said, we know that the square root of 2x plus 4 can only take positive values or 0. So now let's check the value 0 itself. So let's check if this square root expression can take on the value 0 for some x element d. So is there an x element d such that the square root of 2x plus 4 equals 0? As we have already found out earlier, the answer is yes. For x equals minus 2, the expression gets 0. Now let's look at the positive numbers. Maybe our expectation is that g of x can take on all possible positive values. Now we want to prove this expectation and first formulate the following claim. We claim that for every y greater than 0, there's an x element r such that g of x equals y. Actually, even if this claim does not turn out to be true, it's still a good way to start, because going along the way we might run into some problems which give us more insights regarding the range. Okay, let's get started. We start by choosing some general y greater than 0. So we choose y greater than 0. And then we try to find a suitable x by simply setting this y equal to our function g. So we set y equals g of x and hope to find a suitable x. So that gives y equals the square root of 2x plus 4. If I square both sides of this equation, it follows y squared equals 2x plus 4. Now if I subtract 4 from both sides, I get y squared minus 4 equals 2x. If I divide by 2 now, I get x equals y squared minus 4 divided by 2. Now we have indeed found this expression, which gives us, for every y greater than 0, the suitable x such that g of x equals y. But we are not done yet, because remember, we have to make sure that x is in the domain of g. We now check, is x element the domain of g? The domain of g was the interval starting at -2 and running until plus infinity. So only the numbers -2 or greater than -2 are allowed. So we have to check if the x in the blue box is indeed greater than -2. Now, because we have chosen y to be greater than 0, as a consequence we have that also y squared is greater than 0. This is why we can do the following sequence of conclusions. We have x equals y squared minus 4 over 2. Now if I replace that y squared by 0, the resulting expression will be strictly smaller than this expression. So replacing by 0 means just that we have minus 4 over 2, which equals minus 2. So let's have a close look again. Because I know that y squared is greater than 0, if I omit y squared up here in the numerator to get this one, where it has been replaced by 0, that expression must be greater than this expression. But this expression is minus 2. So altogether we have x is greater than minus 2. In other words, we have just confirmed that x indeed is an element of d of g. Bringing all of our partial results together, we conclude that the range of g, is equal to 0 as well as all positive real numbers. We write this using set notation, 0, infinity, and again, infinity is excluded, so we use these brackets. Now let's talk a bit about graphs of functions. A graph of a function is a very helpful tool to illustrate or quickly picture the function in its entirety and understand its basic features. The values for the independent variable, typically x, are spread out here on the horizontal axis, the x-axis, whereas the corresponding function values are spread out here along the vertical axis. The rule of how to assign to a given x value a y value is defined by the graph itself, which is the blue curve in these images. It's read like this, that for instance for a value of 0 we assign that value which is the height of this graph. So that means if you want to know which value does the function have at, say, x equals 0, we draw a vertical line starting at 0 up to the graph, and then we draw a horizontal line from that intersection until it meets the vertical axis. The value of the intersection with the vertical axis is the function value of 0. So the function value of 0 is 0. The function value of 2 is 2. And the function value of minus 2 is minus 2. That is not surprising for a function which is defined as y equals x. In this collection we have drawn some more graphs of very well-known functions. For instance, the so-called normal parabola, which belongs to the function y equals x squared. And that is also a parabola, but it's a cubic parabola and belongs to the function y equals x to the third power. This is the square root function, and the graph of the square root function looks like this. It's important to realize that the negative x values don't have any graph above them. That means they don't belong to the domain of that function. That function here is y over x, and its graph is a so-called hyperbola. Finally, this function depicts the graph of the absolute value of x. As the absolute value doesn't change the numbers for positive numbers, that is just the so-called identity function for the positive values. However, as it does change negative values by taking away the negative sign, that is the negative identity function for the negative numbers. Admittedly, this was just a quick glance at these functions and their graphs. We will dive into these functions in more detail in later videos. To conclude this video, I want to explain this illustration to you. It shows quite nicely how we can picture the domain and the range of a function when using a graph. Remember, the domain of the function are exactly those real values for which the function is defined. That is depicted by that red section here on the x-axis. This red section on the x-axis is the domain of f. On the other hand, the range of the function was defined as the set of all values which occur as function values of the function. That is depicted by the red line here on the vertical axis. So that red segment of the vertical axis is the range of f. That's it for this video. Thanks for watching and see you next time.